Last time we started section 14.4, which was surface areas, and we had looked at the surface areas of several different kinds of shapes. The one that we are now on is the surface area of a cone. All right, so the surface area of a cone is the lateral area plus the area of the base. It looks a lot like the sort of basic formula that we talked about over here for a pyramid, right? Lateral area plus the area of the base. So when we're looking at this, we want to figure out then what is the lateral area and what is the area of the base. This one's a little bit harder to sort of decide and see where the pieces came from. But I think you can do the area of the base just fine. So let me tell you what the lateral surface area is. It's pi r L. Do you remember L is the slant height? Okay, so it's the height from the apex down to the edge of the circular part of the base, not straight to the middle of the base. That would be the height. So they're going to call that the L, the slant height. Does anybody know what the area of the base here would be? The area of a circle. Yeah, and it's pi r squared. So this area of a cone is a very specific type of cone. It is a right circular cone. Agreed? And if you'll remember, I don't know if you will, but some of you encountered a question, well, all of you encountered a question, some of you encountered trouble with the question on the first exam of drawing a cone that had a non-circular base. And it certainly can be done. You can draw anything you'd like on the base of it, it's just that it's not a polygon. And that's what makes it something that's going to end up being a cone. So this one would be specifically for the area of a cone, this formula anyway, because I wrote the pi r squared in here for the area of the base. So if you didn't have a circle on the bottom, if it were an oval, say, you just have to change that portion of this formula, and then you could still use the rest of it. All right, a sphere. So a few details about a sphere. We have something called a great circle, and a great circle is a circle on the sphere whose radius is the same as the radius of the sphere. So how many great circles are there? There are infinitely many great circles for every sphere. Basically, it would be a circle that cuts the sphere into two exact halves, right? So imagine taking a basketball or a globe or something that's got that circular pattern, and you cut it exactly in half. That place where you cut it exactly in half would have formed a great circle. A sphere has infinitely many congruent great circles. And you can think about these as lines of longitude. Okay, so lines of longitude on our globe. But latitude doesn't work. Why is it longitude and not latitude? Do you remember the difference between the two?
Isn't latitude going vertical?
That's backwards.
Oh, never mind.
Longitude goes vertical, like North Pole to South Pole. What does latitude do? It's horizontal, and the latitude lines are parallel to each other, right? So if you were to use latitude lines through like the equator, that would be a great circle. That one's okay. But the latitude line, say for instance, through where we are, would not cut the circle into two equal circles, or two equal halves of the circle, right? Okay, so that's why latitude doesn't work. Longitude works because it's actually intersecting circles, isn't it? They all go through the horizontal, or through the North Pole and the South Pole. So we actually do get infinitely many great circles even just looking at the longitude lines. And we have others as well. It wouldn't have to go through any of the poles or the equator, right? It just has to go through the center of the Earth. That's the only condition, the center of the Earth. All right, the formula for the area of a sphere. Does anybody remember, surface area of a sphere, does anybody happen to remember it?
Isn't it like
4? You remembered well. Good job, Ashley. Yeah, it's 4 pi r squared. The pi r squared shouldn't surprise us, right? That's area of a circle. So a circle or a sphere in some sense is a three-dimensional circle. So that shouldn't surprise us when we're looking at surface area. And then we get the 4 on there as well. All right, so we're going to do an example, and it's kind of a real-life example. And now you're all going to want to go to Brahms when I'm done. Okay? I want to go to Brahms right now. Let's do it. Find the surface area of this ice cream cone, and we're going to make some assumptions about the ice cream cone that aren't really true in real life, okay? So we're making the assumption, this is really more like a snow cone shape, honestly, right? Where we've got a perfect semicircle or half sphere on top, not semicircle, a hemisphere on top, And then on the bottom, we actually have that perfect right cone cylinder. Okay, right cylinder cone. So this isn't the cake cone or something like that. It's a perfectly created cone. So more like a snow cone, really. All right, so this object has two parts to it that are neither one completely the images we've talked about, right? So the object on top is not a sphere. It's a what? It's a half of a sphere. So we have a half sphere on top. So I'm just jotting down, these are kind of like notes for what's going on here. We have a half sphere on top. So we need the surface area of that. Plus what do we have on the bottom? We have a cone, but just the lateral area of the cone, right? Well, let me put it this way. We've got a cone, and then in parentheses I'll put, or underneath it I'll just put lateral area. So lateral. So we want to make sure that we only use the pieces that we need. So what is the formula for the surface area of a sphere? We just did it. 4 pi r squared. So what will be our part of that we need? Yeah, divided by 2, so it'd be 2 pi r squared, right? Because we just have a half sphere on top. All right, now the cone we had over here, there was 2 pieces of it. This piece at the end was the surface area of the base, right? And this piece right here in the middle was the lateral part. So we don't want all of this formula. We just want the lateral part. So we just want the pi RL.
Why don't we do the base part?
Because the surface area is just the area on the surface. The base of the cone would be inside of this object. Yes, we only want the outside surfaces. And so imagine sort of like, you guys ever seen the, okay, so this isn't exactly this shape, but you can imagine it like this. Have you seen the arts and crafts projects where you blow up a balloon and you wrap it in string? And then you coat the balloon with the string in some kind of a glue base. And then once it's dry, you pop the balloon. Is everybody with me? Even if you haven't seen this before, can you picture what I'm describing? That piece on the outside, that's the surface area, right? It's the shell part of it. And on this one, if we did the same thing, if we had this shape and we wrapped it up in string, that base of the cone would have been inside. It wouldn't be covered with string. So, all right, we have all these pieces, I think. What is R? It's 4. So we have 2 pi and then 4 squared plus pi times 4. And what's L? Oh, we got to find that one. So we weren't given that one. You're right. Okay. Can we find that? Yes, we can with the Pythagorean theorem. Very good, Brendan. Okay. How about we mark out our triangle, and I'll mark it in red. Here is the triangle that we're working with. In this triangle, we know the legs of the triangle, correct? So how would I set up the formula to find the side, this lateral area that we want? I'll call it L. Say again, Morgan?
4 squared plus 8 squared.
4 squared plus 8 squared equals C squared or L squared. I just labeled it L since we used L on the other part of our formula. All right, 4 squared is 16. 8 squared is, and then we've got our L squared. What's 64 plus 16? 80. And this would then be L squared, and we're taking a square root. For the time being, I'm just going to leave it as square root 80, okay? Because we don't really care about that value. We care about using that value. Are you with me? So I've just put the square root of 80 into the formula there. Now, just like we talked about in class last time, your book may actually give this answer in terms of pi, but this would be a very awkward thing to give this answer in terms of pi for, because the problem is a very application-based problem, right? So I'm not interested in having the pi in the problem when we give our answer. I'd like to have it all multiplied out with a couple decimal places, okay? So go ahead, take your calculator. Parts of this we can simplify, I suppose. We could write down that 4 squared is 16, right? This piece is 16, and then times the 2 at the beginning would give me 32 pi. And then we can write this 4 square root of 80 pi. As long as you remember that the pi is not underneath the radical, we'll be okay. All right, and we're looking for a decimal approximation for this.
212.93
Okay. Did everybody get that value as you're calculating with your devices? Yes?
I didn't, but I didn't use the calculator, so I was close. I got 212.6, 2.6.
You know what? If we all calculated that close without a calculator, I think we'd be doing really well, Brendan. So that's very good.
Because I approximated on the square root of 80, so that's.
Gotcha. That makes sense. Okay, anybody not get that answer with your calculator? Did you get it, Morgan?
Yeah.
Okay. All right, any questions on this one? All right.